Imagine spending an entire year designing a new commercial building. Planning approval is secured, coordination is complete, the client signs everything off, then your compliance software produces just one word: failed. Not because you've made a mistake, not because you've broken building regulations, but because the rules themselves have changed. That is exactly the situation many design teams could soon face as the future building standard comes into force across England. And the changes go far beyond replacing a gas boiler with a heat pump. They're changing the very shape of our buildings. The future building standard doesn't simply prohibit gas boilers. Instead, it changes something much more fundamental: the compliance benchmark itself. The new notional building assumes highly efficient electric heating supported by solar photovoltaic generation. That means traditional gas-based designs become increasingly difficult to justify through compliance modeling. The software isn't making a political decision, it's simply comparing your building against an entirely different benchmark. The regulations were laid before Parliament on the 24th of March 2026. Following a 12-month implementation period, the new standards will come into force in March 2027. That gives the industry a limited window to prepare, because these aren't small specification changes. They're changing mechanical design, electrical infrastructure, architectural coordination, and even structural planning. Today we're focusing on 3 engineering changes that every building services professional needs to understand. First, why low-temperature heating completely changes the spatial requirements of buildings. Second, how mandatory solar photovoltaic systems reshape electrical design. And finally, why compliance modeling has become dramatically less forgiving than many engineers realize. If you're involved in building services, architecture, or construction, these changes affect projects from the earliest design stages. So let's begin. For decades, building services engineers designed around high-temperature heating systems. Flow temperatures of around 80 degrees Celsius allowed compact pipework, relatively small emitters, and efficient use of valuable plant space. Heat pumps operate very differently. To achieve their highest efficiencies, they typically work with much lower flow temperatures, often around 55 degrees or lower. That seemingly simple change has consequences that ripple through the entire building. The laws of physics haven't changed, but our design assumptions have. When water carries less heat per liter, we need to move more of it through the building to deliver the same heating output. Higher flow rates mean larger pipes. Larger pipes require larger risers. Larger risers compete for ceiling space with ventilation ducts, cable trays, drainage systems, and structural beams. What once seemed like a simple equipment substitution quickly becomes an exercise in multidisciplinary coordination. The real challenge isn't the heat pump, it's finding somewhere to put everything that comes with it. So, low-temperature heating means larger flow rates, larger distribution pipes, and drastically bigger risers. But the spatial battle doesn't end in the ceiling voids. In fact, it's about to get much tighter, because when you move away from fossil fuels, you also lose the ability to generate hot water instantaneously. In part 2 of this video series, we will look at the cylinder problem, the massive thermal storage units heading for your plant rooms, the rooftop revolution that's rewriting structural layouts, and why REBA Stage 2 coordination is no longer optional. Please subscribe to be notified about other videos in this series.